Okay, in this lecture video, we're going to be talking about line and surface integrals. This is divided up into two sections. The first, we'll introduce briefly what line and surface integrals are, and in part two, we'll talk about how they relate to surfaces and volumes when you substitute into these integrals. Now, I should note that in this course, the idea of setting up these integrals is not so much to learn the tricks for making triple integrals analytically. The idea is that you learn how it works so that you can numerically solve problems, as is more common in engineering. I'm going to be saying more about that as we advance, but don't sort of freak out at the idea of doing a triple integral. It'll be presented a little bit differently in this course. All right, so let's take a look at what we mean by a line integral. A line integral would be, for example, if we have a path, right? Let's say you're walking along a trail in a park, and this line right here, this zigzagging line represents the path of this trail in a park. And someone asked you the question, how far to the east has this path gone? Then one way you might solve it is with a line integral. And so the way this will work is at any location along this path, you would take a vector that basically points in the direction of the path. And let's say this vector is A, right? A represents the direction of the trail at any location. And we're interested in the eastward direction, and the eastward direction is going to be x hat. All right, so the way to think of it is, in each of these little steps, if we divide up this path into little pieces, in each step, there's a little contribution to whether you're moving eastward or westward. And all we really want to do is sum up all those little contributions. And summing up little contributions, that's the same as an integral. All right, so we're going to start out with an integral. And now we're going to ask the question of what is the contribution of one very small piece of this. And so if we take this vector A and we make it really, really small, then basically we can write this as dA, right, a small vector in the direction of A, times A hat, right? So this is a scalar right here, right? dA is a scalar, and it's pointed in the A direction, right? So this is the contribution of one path, or this is the small vector that's in the direction of the path. So the contribution to the east-west direction, in order to do that, we want to pick out only the component that is in the east direction. And so we're going to take the dot product with x hat, a vector that goes in the x direction. All right, so then what we're next going to do is we're going to place that into the integral. So this will be a hat dot x hat dA. All right, and the order of this doesn't matter. The dA can go on either side. It still works out the same since this is a dot product. And then we have the limits of this integral will simply be the beginning and the end. We need some sort of parameter that traces the path, right? Maybe it's the actual length along the path. The actual path may be a mile long. It could be that, or it could be if you're walking along the path as a function of time. It could be time as well. But I'm just going to put here beginning to end, and this is how we might set up an integral. Now, for this to actually be calculated numerically, you would need to know what is the vector A hat as a function of whatever this parameter is. All right, but this would give us the total eastward motion. All right, so A hat is going to be a function, right? A hat is a function. It's going to vary along the path. And you need to represent that in some way. It could be that you represent this with some function f of x, right, which will take on some value. Maybe it's a quadratic or a zigzagging back and forth. But you have to represent anything that's inside this integral, and sort of place that inside the line integral. So the idea of a line integral is that it only picks out the components that are in the preferred direction. And that preferred direction in this case is indicated by this dot product. All right, so that's a line integral. All right, a surface integral is a little bit different. A surface integral is the following. We're talking about vectors in particular. Right? We're going to see surface integrals in the following way. Let's say we've got a little window right here. Right? You're in your house and you open your window, and it's a windy day. And so on this particular day, you've got wind blowing in or maybe out of your window. And someone asks you the question, what's the total flow of air that is coming out of your window or is going through your window? All right, for that, you'd want to have some measure of the flow of air, which may well be different. It could be that there's a lot of flow on one side of the window and less on the other, or maybe there's a lot in the middle and not much on the outside. But anywhere in the window, you have a definition of what the total flow is. And the surface integral is integrating that flow of air across the entire window. But in doing so, we're only going to care about the component that is through the window, right? So if you've got wind that's sort of parallel to the window or alongside the window, then we're basically going to ignore that. We don't really care about that component. We do, however, care about a component that is through the window. So this is going to be important, right? That we want to capture in this surface integral. So the way we might set this up is with an integral. And because this is a two-dimensional integral, I'm going to put two different bars here. And we're going to have some measure of airflow as a vector. And we're going to take a dot product of ds. All right, S is a basically small representation of surface area. Since we're taking the flow in one little square within this window, and we're integrating all of those little pieces, all those little small scale contributions are all going to add up to give us the total flow of air. So in this case, ds is going to be a vector that is through the surface. And so airflow dotted with ds is only going to be sensitive to the component of airflow that is through the boundary. It's not parallel to the window, but is specifically through the window. So this formulation right here is going to pick out the component of airflow that is going to contribute to the total flux of air in and out of your window. And the magnitude of ds will be some small piece of area. All right, so for a Cartesian coordinate system, if we set up a coordinate system like this, where we have x and y as our coordinate system, then the small piece of area would be dx times dy. All right, since this small segment would be dx, this small segment would be dy, and so the area of this small square is just a product dx times dy. All right, so ds just has that sort of differential piece of area to it. All right, and that is a surface integral. We'll see this in a couple of contexts. All right, so in the next lecture video, we're going to talk specifically about what we might use to substitute for this ds depending on which coordinate system we're using, and we'll try to do that fairly briefly, since it's not the kind of thing you really need to memorize, but it is the kind of thing you need to understand. So hold on to that, and we'll cover that in the next video. But hopefully in this video, we've given you a good introduction to what a line integral and a surface integral is in terms of summing up specific types of contributions of vectors to certain quantities.